September 13th, 1942, 2:47 a.m. A remote valley in eastern Tennessee, where the Clinch River cuts through ancient Appalachian ridges. Colonel James C. Marshall stood in ankle-deep mud, watching bulldozers tear into virgin forest under floodlights that turned night into day. Around him, an army of workers moved like ants, clearing timber, grading roads, pouring foundations for structures whose purpose they would never know. In his briefcase lay blueprints for the largest construction project in human history, a city that would consume more electricity than New York, a facility that would cost more than the entire American automotive industry, a secret so vast that 125,000 people would work there and fewer than a dozen would understand what they were building. They called it Site X, the Manhattan Engineer District, Clinton Engineer Works, but none of those names captured the audacity of what was happening in this Tennessee valley. America was building a city from nothing in 18 months to produce a material that existed only in theory. The workers clearing brush didn't know they were creating the most expensive military installation ever conceived. The engineers surveying land didn't know their calculations would determine the fate of 500,000 lives. The security guards checking identification didn't know they were protecting the future of warfare itself. What Marshall knew, what kept him awake at night, was that failure meant Germany would get there first, that Adolf Hitler would possess a weapon that could erase cities, that the war, already the bloodiest in human history, would end with mushroom clouds over American soil. The mathematics were brutal. Germany had a 2-year head start. German scientists had discovered nuclear fission. German engineers were experimenting with uranium enrichment. German industry, though battered by Allied bombing, still possessed technical sophistication that America struggled to match. But Germany didn't have what America had: unlimited space, unlimited resources, unlimited willingness to bet everything on a weapon that might not work. The site Marshall was building would require more concrete than any project in history, more steel than a fleet of battleships, more copper than existed in the entire National Reserve, and all of it had to be built in secret, in 18 months, in a location so remote that workers would need an entirely new city just to house them. The irony was perfect. The most advanced weapons program in human history would be built in a place that didn't exist on maps, where residents had farmed the same land since before the Revolution, where electricity was a luxury and paved roads were non-existent. The United States government was about to displace 3,000 families, erase their communities, and replace them with industrial facilities so large they would consume 1/7 of all electricity generated in America. This is the story of Oak Ridge, the secret city, a place built by people who didn't know what they were building, operated by workers who couldn't tell their families where they worked, creating a material so rare that the entire facility would run for 3 years to produce enough for 3 bombs. The story of how American industrial might, applied with terrifying focus, transformed theoretical physics into practical genocide. How 59,000 acres of Tennessee farmland became the birthplace of the atomic age. How ordinary Americans, following orders they didn't understand, enabled destruction on a scale previously unimaginable. The chain of events that led to Oak Ridge began in a squash court beneath the University of Chicago's football stadium on December 2, 1941. Enrico Fermi, an Italian physicist who had fled fascism, watched instruments monitor the world's first controlled nuclear chain reaction. Chicago Pile 1, as it was designated, consisted of 400 tons of graphite, 50 tons of uranium oxide, and 6 tons of uranium metal stacked in a precise lattice that allowed neutrons from splitting atoms to strike other atoms, sustaining a controlled release of energy. The physics were elegant. Uranium-235, a rare isotope comprising only 0.7% of natural uranium, could sustain a chain reaction. When struck by a neutron, a U-235 nucleus split, releasing energy and additional neutrons. If those neutrons struck other U-235 atoms, the reaction continued. In a reactor, control rods absorbed excess neutrons, maintaining steady power output. In a bomb, removing those controls would cause the reaction to accelerate exponentially, releasing energy equivalent to thousands of tons of TNT in microseconds. The problem was scale. Natural uranium contained only one atom of U-235 for every 140 atoms of U-238, the non-fissile isotope. Separating them was theoretically possible, but practically nightmarish. The two isotopes were chemically identical, differentiated only by a mass difference of 3 neutrons, a variance of 1.3%. Conventional chemical separation was impossible. Any physical separation method would require processing tons of uranium to produce grams of weapons-grade material. Multiple separation methods existed, each with catastrophic limitations. Electromagnetic separation used gigantic magnets to bend uranium ions along slightly different paths based on mass, allowing collection of separated isotopes. But each calutron, as the machines were called, could process only milligrams per day. Gaseous diffusion involved converting uranium into uranium hexafluoride gas, then forcing it through microscopic barriers that allowed lighter U-235 molecules to pass slightly faster than heavier U-238. But this required thousands of stages, each adding minimal enrichment, and consumed staggering quantities of electricity. Thermal diffusion used temperature gradients to separate isotopes. Liquid thermal diffusion involved pumping uranium hexafluoride through tall columns with heated inner walls and cooled outer walls, creating convection currents that concentrated lighter isotopes at the top. But the process was slow, inefficient, and required massive infrastructure. Centrifuge separation spun uranium hexafluoride at extreme speeds, using centrifugal force to separate isotopes by weight. But reliable high-speed centrifuges didn't exist in 1942. Leslie Groves, the Army Corps of Engineers general assigned to lead the Manhattan Project in September 1942, understood that America's advantage wasn't scientific sophistication, it was industrial brutality. Germany had better physicists, but America had Tennessee Valley Authority hydroelectric dams, American factories, American construction capacity. Groves decided to build everything simultaneously, all separation methods at maximum scale, redundantly, wastefully, with no regard for efficiency or cost. The site selection criteria were specific: near TVA power generation for unlimited electricity, remote enough for security, large enough for massive facilities, with rail access for shipping, with water for cooling, with minimal existing population to displace. Oak Ridge, Tennessee, or rather the valley where Oak Ridge would be built, met every requirement. The area was served by Norris Dam and the TVA grid. It was isolated in Appalachian foothills far from population centers. It had 59,000 acres of available land. The Southern Railway ran nearby. The Clinch River provided cooling water. Only 3,000 families lived in the designated area, and they could be removed. On September 19, 1942, the federal government began condemnation proceedings. Residents received letters informing them they had weeks to vacate land their families had occupied for generations. Fair market value would be paid, eventually, through legal processes that would take years. Resistance was futile. The War Powers Act gave the government unlimited authority to seize property. Families abandoned homes, farms, schools, churches, cemeteries. Communities that existed since the 1790s ceased to exist. By January 1943, the valley was empty. What happened next defied comprehension. Construction began simultaneously on multiple facilities before designs were finalized. The electromagnetic separation plant, designated Y12, would cover 825 acres and house 1,152 calutrons arranged in racetrack configurations. Each calutron required a magnet weighing 10,000 tons, with copper coils carrying 95,000 amperes, generating magnetic fields of 5,000 Gauss. The silver required for electrical windings exceeded America's entire copper reserve, forcing the Treasury Department to loan 14,700 tons of silver from the national reserves. The gaseous diffusion plant, designated K25, would be the largest building on Earth. A U-shaped structure covering 44 acres under a single roof, containing 4,000 stages of uranium hexafluoride diffusion. Each stage required a pump, a heat exchanger, and a diffusion barrier with billions of microscopic holes, each precisely 100 angstroms in diameter, small enough to allow molecular separation but large enough for gas flow. The barrier material didn't exist. Scientists experimented with sintered nickel powder, deposited nickel on bronze mesh, and electroformed nickel tubes. Nothing worked reliably at scale. The thermal diffusion plant, designated S50, would consist of 2,142 vertical columns, each 48 feet tall, arranged in 21 racks. Steam-heated inner pipes to 600 degrees Fahrenheit while cooling water chilled outer walls to 50 degrees Fahrenheit, creating temperature gradients that separated isotopes through thermal convection. The plant would consume steam from coal-fired boilers at rates exceeding any existing industrial facility. The plutonium production reactors, designated X10, represented yet another approach. Instead of enriching U-235, these air-cooled graphite reactors would transmute U-238 into plutonium-239 through neutron bombardment. Plutonium was fissile like U-235, but chemically distinct, allowing separation through conventional chemistry rather than physical separation. Construction proceeded 24 hours daily. At peak, 75,000 construction workers lived in the valley, housed in temporary barracks that became the fifth largest city in Tennessee. They built roads, railroads, power stations, water treatment plants, sewage systems, telephone networks, fire stations, hospitals, schools, stores, and churches, everything required for a city of 75,000 plus the secret facilities those residents would operate. The scale was incomprehensible. Workers poured 1 million cubic yards of concrete, enough to build a sidewalk from Oak Ridge to Los Angeles. They installed 10,000 miles of electrical wiring. They laid 300 miles of roads. They built 300 miles of fences, many electrified, patrolled by armed guards with orders to shoot intruders. Security was absolute. The entire site was fenced and guarded. Every worker required clearance. Everyone who entered was searched. Cameras were forbidden. Writing was restricted. Telephone calls were monitored. Mail was censored. Anyone asking questions about the facility's purpose was investigated. Workers were told only what they needed to know to perform their specific tasks. Calutron operators knew they were separating isotopes, but not what isotopes or why. Engineers knew systems, but not overall purpose. Operators knew procedures, but not context. Only a handful of senior leaders understood the complete picture. Even within facilities, workers were segregated. The Y-12 electromagnetic plant employed 22,482 workers at peak, but each section was isolated. Workers entering the Cafeterias halls saw thousands of identical machines arranged in curved rows, each tended by operators monitoring dials and adjusting controls according to checklists they didn't understand. The machines themselves were marvels of desperate engineering. Each alpha cafeteria weighed 3,000 tons, with copper coils wound on iron cores that had been painstakingly demagnetized before winding to prevent interference. Silver borrowed from the treasury was fabricated into strips, then wound into coils carrying currents that generated magnetic fields powerful enough to bend ions through precise arcs. Uranium was heated to 1100 degrees Fahrenheit in graphite crucibles, ionized by electron guns, then accelerated through the magnetic field. Lighter U-235 ions curved along a tighter path than heavier U-238, allowing collection in separate receivers. The process was fantastically inefficient. Each alpha cafeteria produced 0.1 grams of 10% enriched uranium per day. To reach weapons-grade concentration, 90% U-235, required further enrichment in beta cafeterias, which processed alpha output through additional magnetic separation. The entire Y-12 complex operating at capacity produced less than 50 kilograms of weapons-grade uranium monthly. A single bomb required 64 kilograms. The electromagnetic process alone would take years to produce enough material for 3 bombs. The gaseous diffusion plant represented a different engineering nightmare. K-25 was designed for 4,000 diffusion stages, each incrementally enriching uranium hexafluoride. The theory was simple. Force UF6 gas through a porous barrier and lighter U-235 molecules would pass through fractionally faster than heavier U-238 molecules. After thousands of stages, meaningful enrichment accumulated, but implementing this required solving problems no one had encountered. Uranium hexafluoride was viciously corrosive, attacking steel, aluminum, and most conventional materials. It had to be kept gaseous, requiring careful temperature control. Any leak would release radioactive and chemically toxic material. The diffusion barriers were the critical bottleneck. Each stage required square meters of barrier material with billions of perfectly uniform holes, each 100 angstroms in diameter. Early experiments with sintered nickel powder produced barriers too fragile for industrial use. Scientists at Columbia University developed a process for electroplating nickel onto aluminum oxide membranes, then dissolving the aluminum to leave a perforated nickel sheet. Production was excruciatingly slow. Each barrier took weeks to manufacture, and K-25 needed thousands. Even after barriers were produced, most failed in service. UF6 gas corroded them. Pressure differentials tore them. Contamination clogged them. Entire sections would fail, requiring shutdown and replacement. The pumps presented equal challenges. Each diffusion stage required a pump to maintain gas flow and pressure differential across the barrier. But UF6 corroded conventional pump seals, bearings, and lubricants. Engineers developed specialized pumps with Teflon seals, graphite bearings, and exotic lubricants, but reliability remained abysmal. Pumps failed constantly, requiring continuous maintenance by workers who didn't know they were handling radioactive material. The thermal diffusion plant, S50, used the simplest physics, but required brutal infrastructure. Steam from coal-fired boilers flowed through inner pipes heated to 600 degrees Fahrenheit. Cooling water from the Clinch River flowed through outer jackets at 50 degrees Fahrenheit. The temperature gradient created convection currents that carried lighter U-235 molecules upward and heavier U-238 downward. After passing through 48 feet of column, partially enriched uranium was collected at the top, while depleted uranium drained from the bottom. The process required staggering energy input. S-50 consumed 100,000 pounds of steam per hour from coal-fired boilers. It processed 5,000 gallons of cooling water per minute from the Clinch River. It operated 2,142 columns continuously, each a towering steel structure requiring precise temperature control. The entire facility was a thermodynamic nightmare, converting heat to marginal isotope separation with efficiency measured in fractions of a percent. But it worked. S-50 produced enriched uranium that could be further processed by other methods, providing crucial feedstock for Y-12 and K-25. The plutonium reactors at X-10 represented yet another technical frontier. These air-cooled, graphite-moderated reactors transmuted common U-238 into plutonium-239 through neutron bombardment. The physics were understood. Neutrons from fission struck U-238 nuclei, converting them to U-239. This decayed to neptunium-239, which decayed to plutonium-239, a fissile isotope suitable for weapons. The advantage was chemistry. Unlike U-235 and U-238, which were chemically identical, plutonium was a distinct element. It could be separated from uranium through conventional chemical processing rather than physical separation. The X-10 reactor, a pilot facility preceding larger production reactors at Hanford, Washington, was a 24-foot graphite cube containing 1,248 uranium slugs clad in aluminum. Air cooling removed heat generated by fission. Control rods regulated neutron flux. After irradiation, uranium slugs were removed and transported to chemical separation facilities where plutonium was extracted through complex solvent extraction processes. The entire operation exposed workers to radiation hazards barely understood. Uranium slugs removed from the reactor were intensely radioactive, emitting gamma rays and beta particles that could kill within hours. Workers used remote handling equipment, long tongs, periscopes, thick shielding to manipulate materials they couldn't safely approach. By late 1943, Oak Ridge had become the fifth largest city in Tennessee, with a population exceeding 75,000. It existed on no maps. Mail was addressed to Post Office Box 1663 with no city name. Residents carried badges color-coded by clearance level. White badges indicated access to all areas. Blue badges restricted workers to specific facilities. Green badges were for construction workers. Security personnel wore no badges. Everyone knew who they were. The city itself was temporary, improvised, insufficient. Housing consisted of prefabricated structures called cemesto houses, flimsy plywood boxes with cement asbestos siding. Thousands lived in trailer parks. Others lived in dormitories, barracks, or hutments, minimal wooden structures with communal facilities. The infrastructure was chaotic. Unpaved roads turned to mud in rain. Water supplies were frequently contaminated. Sewage systems overflowed. Power outages were common despite unlimited access to TVA electricity. The town had movie theaters, bowling alleys, churches, schools, and stores, everything needed for a city, but all of it felt temporary, like a military camp waiting for the war to end. Workers arrived daily by the hundreds, drawn by war industry wages that exceeded anything available in depression-ravaged Appalachia. They came from farms, from small towns, from unemployment lines. Most were women. With men drafted for military service, women operated the cafeterias, maintained the equipment, monitored the processes. They became the backbone of Oak Ridge operations, performing technical work requiring precision and discipline. The work itself was mind-numbing. Cafeteria operators sat at control panels watching dials, adjusting settings to maintain ion beam current, source temperature, and receiver position. They worked 8-hour shifts in climate-controlled facilities, never knowing that the isotopes they were separating would become the cores of atomic weapons. The tedium was interrupted by equipment failures. Ion sources would burn out, receivers would saturate, vacuum pumps would fail. When failures occurred, maintenance crews entered the Calyutron tanks wearing protective gear, working in confined spaces contaminated with uranium dust and beryllium powder, neither understood as toxic at the time. The gaseous diffusion plant operated continuously, but unreliably. Entire cascade sections would fail when barriers ruptured or pumps seized. Engineers fought constant battles with corrosion, contamination, and mechanical failure. Operators monitored pressure gauges, temperature readings, and flow rates, making adjustments that marginally improved enrichment efficiency. Production was measured in grams per day, incremental progress toward weapons-grade material that required kilograms. The thermal diffusion plant ran 24 hours daily, consuming coal and water at rates that defied sustainability. Workers monitored steam pressure, cooling water flow rates, and product withdrawal rates. Column failures were frequent. Thermal stress would crack welds, corrosion would perforate pipes, contamination would clog valves. The X-10 reactor, relatively reliable by Oak Ridge standards, operated on 3-week cycles. Uranium slugs were loaded, irradiated for 21 days, then removed for chemical processing. Each slug became radioactive enough to be lethal at close range. Workers used remote handling equipment to transfer slugs from the reactor to shielded casks, then transported them to chemical separation facilities. The separation process used concentrated nitric acid to dissolve irradiated uranium, then organic solvents to extract plutonium through liquid-liquid extraction. The chemistry was complex, the hazards severe, the yields marginal. Life in Oak Ridge was surreal. Workers lived in a city that didn't officially exist, performing jobs they couldn't discuss, producing materials whose purpose was classified. They couldn't tell families where they worked. They couldn't describe their duties. They couldn't explain why Oak Ridge consumed more electricity than most American cities, despite having no visible industry. The questions haunted them. Why were they separating isotopes? What was the purpose of facilities consuming infinite resources to produce grams of material? Why such security? Why such urgency? Most suspected they were producing poison gas or synthetic rubber or some other war material. Some guessed they were refining uranium for armor plating or radar components. A few suspected the truth, but said nothing. The penalties for discussing classified information were severe: immediate dismissal, possible prosecution, public disgrace. Workers learned to accept compartmentalization, to do their jobs without asking why, to trust that their labor served some larger purpose they weren't privileged to understand. The breakthrough came in February 1945. After 2.5 years of operation, Y-12 had produced 50 kilograms of weapons-grade U-235, enough for one bomb. K-25, finally operating reliably after years of barrier failures and pump replacements, was enriching uranium to intermediate concentrations that could be finished in Y-12 calutrons. S-50 was providing low-enrichment feedstock that accelerated the cascade. The 3 processes operating in series achieved production rates that would have been impossible individually. On February 24, 1945, the first shipment of weapons-grade uranium left Oak Ridge in an unmarked convoy, destination Los Alamos, New Mexico. The material represented 3 years of labor by 75,000 workers, 3 years of consuming 1/7 of America's electrical production, 3 years of processing tens of thousands of tons of uranium ore through facilities covering hundreds of acres, all to produce enough enriched uranium to fill a softball. The irony was perfect. Oak Ridge, the largest industrial facility on Earth, had produced less material than a single worker could carry. But that material would become Little Boy, the uranium gun assembly bomb that would destroy Hiroshima on August 6, 1945, killing 70,000 people instantly and another 70,000 from radiation and burns over subsequent months. The bomb itself was simple, almost crude. A cylinder of weapons-grade U-235 would be fired into another cylinder of U-235 using a conventional gun mechanism. When the two pieces came together, they would form a critical mass. The chain reaction would begin. In less than a microsecond, the supercritical assembly would release energy equivalent to 15,000 tons of TNT. Oak Ridge workers didn't learn what they had built until August 7, 1945, when newspapers published photos of Hiroshima's destruction. The revelation was devastating. Workers who had operated calutrons without knowing their purpose discovered they had enabled genocide. Women who had monitored dials and adjusted controls realized they had participated in creating a weapon that could erase cities. Maintenance crews who had repaired equipment in radioactive facilities understood they had helped build the bomb. The reactions were complex: pride that their labor had contributed to ending the war, horror at the destruction they had enabled, relief that the secret burden they had carried was finally revealed, anger that they hadn't been trusted with the truth. Some quit immediately, others continued working, processing the knowledge that their technical labor had facilitated mass death. A few suffered psychological breaks, unable to reconcile their self-image with their role in producing atomic weapons. The scale of Oak Ridge operations continued to expand after Hiroshima. Production increased, new facilities were built. By 1947, Oak Ridge employed 82,000 workers and produced enriched uranium for weapons stockpiling and reactor fuel. The temporary city became permanent. Cemesto houses were replaced with conventional construction. Roads were paved, infrastructure was upgraded. Oak Ridge transformed from a wartime secret facility into America's permanent uranium enrichment center. The statistics of Oak Ridge construction and operation defied comprehension. Total construction cost exceeded $1.2 billion in 1940s dollars, equivalent to roughly $18 billion today. The site consumed 59,000 acres. Construction required 1 million cubic yards of concrete, enough to build a highway from Oak Ridge to Knoxville. Workers installed 386,000 cubic yards of asphalt and gravel. They laid 56 miles of railroad track. They built 55,000 individual structures. At peak operation, Oak Ridge consumed 238,000 kilowatts of electricity continuously, more than most American cities, despite having a population of 75,000 people. The U-12 electromagnetic plant alone covered 825 acres and housed 1,152 calutrons. At peak operation, it employed 22,482 workers operating equipment that consumed 57,000 kilowatts of electricity. The calutron magnets contained 14,700 tons of silver borrowed from the U.S. Treasury, silver that was eventually returned, though slightly contaminated with uranium. The K-25 gaseous diffusion plant covered 44 acres under a single roof, at the time the largest building on Earth. It contained 4,000 diffusion stages, each with custom fabricated barriers, pumps, and heat exchangers. The facility consumed 120,000 kilowatts of electricity continuously. The S-50 thermal diffusion plant operated 2,142 columns arranged in 21 racks, consuming 100,000 pounds of steam per hour and 5,000 gallons of cooling water per minute. The X-10 plutonium production reactor, though smaller than later Hanford reactors, represented the world's first continuously operated nuclear reactor. The human cost was equally staggering. 3 years of continuous construction killed 365 workers in industrial accidents. Hundreds more were injured. Long-term radiation exposure would kill dozens more over subsequent decades, though exact numbers remain classified. The workers who operated Oak Ridge facilities were exposed to hazards that wouldn't be fully understood for decades. Uranium dust coated equipment and filled the air in processing areas. Beryllium, used in reactor construction, caused chronic lung disease. Radiation from enriched uranium and plutonium caused cancers that wouldn't manifest for years. Workers handling irradiated materials received doses exceeding modern safety limits by orders of magnitude. The health monitoring was primitive. Workers wore film badges to measure radiation exposure, but dosimetry standards were crude. Medical surveillance was minimal. Long-term health effects were unknown and largely ignored. The security apparatus that controlled Oak Ridge was equally unprecedented. The site was patrolled by 2,000 armed guards. Fences, many electrified, surrounded the entire facility. Watchtowers provided continuous surveillance. Every person entering required clearance. Every vehicle was searched. Every package was inspected. Telephone calls were monitored. Mail was censored. Informants reported suspicious conversations. Security personnel maintained files on thousands of workers, tracking associations, political beliefs, and personal behavior. The paranoia was justified. The Manhattan Project represented the most valuable military secret in history. If Germany or Japan learned the details of uranium enrichment or plutonium production, they might replicate the process. If they discovered the bomb's design, they might build their own. Every worker represented a potential leak. Every document was a vulnerability. Every piece of equipment leaving the site could reveal technical details. The security measures, though oppressive, were considered necessary to protect information worth more than any physical asset. The ethical questions were deferred until after Hiroshima. During construction and operation, workers focused on technical challenges, production quotas, and immediate problems. The moral implications of building atomic weapons were irrelevant to engineers solving diffusion barrier fabrication or operators maintaining caluitron ion sources. Only senior leaders knew the ultimate purpose, and they considered the ethics settled. Anything that ended the war faster was justified. After Hiroshima, those ethical questions became unavoidable. Had Oak Ridge workers participated in a necessary evil or enabled atrocity? Was the atomic bomb a justified weapon that saved American lives by making invasion of Japan unnecessary, or was it a war crime that killed 140,000 civilians? Were the workers heroes who helped end history's bloodiest war, or were they accomplices to mass murder? The questions had no clear answers. Many workers struggled with moral ambiguity for the rest of their lives. They were proud of their technical achievements but haunted by the results. They believed they had done necessary work but were horrified by the destruction they had enabled. The scientific community was similarly divided. Robert Oppenheimer, scientific director of Los Alamos, famously quoted Hindu scripture after witnessing the first atomic test. "Now I am become death, the destroyer of worlds." Many Manhattan Project scientists later became advocates for nuclear arms control, arguing that the weapons they had created must never be used again. Others defended atomic bombings as military necessities that saved hundreds of thousands of lives by forcing Japan's surrender without invasion. The strategic impact of Oak Ridge and the Manhattan Project extended far beyond Hiroshima and Nagasaki. The atomic bomb fundamentally altered warfare, diplomacy, and international relations. It created the doctrine of mutually assured destruction, the recognition that nuclear powers could annihilate each other, making major war between them suicidal. It drove the Cold War arms race as the Soviet Union rushed to develop its own atomic weapons. It led to proliferation as more nations sought the ultimate deterrent. Oak Ridge itself remained operational long after World War II ended. The uranium enrichment facilities continued producing material for weapons stockpiling and reactor fuel. New facilities were built for isotope separation and nuclear research. The temporary secret city became a permanent government installation. The population stabilized around 30,000. The infrastructure was upgraded to permanent standards. Oak Ridge transitioned from wartime crash project to Cold War nuclear production center. The technological legacy of Oak Ridge was profound. The electromagnetic separation process pioneered in Y12 calutrons became the foundation for modern mass spectrometry. The gaseous diffusion process, perfected in K25, remained the dominant uranium enrichment method until centrifuge technology matured decades later. The plutonium production techniques developed at X10 were scaled up at Hanford and later facilities worldwide. The remote handling equipment developed for radioactive materials became standard in nuclear facilities globally. The industrial achievement represented by Oak Ridge remains unmatched. No facility before or since has been built so quickly, at such scale, with such technological ambition, under such secrecy. The Manhattan Project compressed development timelines that would normally span decades into months. It deployed technologies before they were proven. It built production facilities before designs were finalized. It succeeded through brute force, unlimited funding, unlimited resources, unlimited labor, and absolute priority over all other war production. The German nuclear program, by contrast, never achieved industrial scale. Werner Heisenberg and his colleagues understood the physics of fission and chain reactions. They recognized that U-235 enrichment could produce weapons-grade material. They experimented with uranium and heavy water. But Germany never committed resources comparable to the Manhattan Project. German facilities were small, underfunded, and vulnerable to Allied bombing. German scientists pursued theoretical understanding rather than industrial implementation. By war's end, Germany's nuclear program had produced nothing resembling a weapon. The Soviet atomic program, informed by espionage that provided Manhattan Project secrets, required 4 years after Hiroshima to test its first atomic bomb. Even with stolen designs and proven enrichment techniques, Soviet scientists and engineers needed years to build the infrastructure, train the workers, and solve the technical challenges. Oak Ridge, built from zero knowledge in 18 months, represented an industrial achievement Soviet industry couldn't match even with complete blueprints. The human stories from Oak Ridge revealed the complexity of the achievement. Thousands of workers came from Appalachian poverty to operate the world's most advanced technology. Farm women from Tennessee and Kentucky became calutron operators, learning to maintain ion beam current and source temperature on equipment whose purpose they didn't understand. Coal miners from West Virginia became maintenance workers in gaseous diffusion plants, repairing pumps handling materials they didn't know were radioactive. Recent high school graduates became laboratory technicians, performing chemical analyses on materials that would become atomic weapons. The training was minimal but effective. Workers received weeks of instruction on equipment operation, then were expected to maintain production standards through repetition and discipline. The work was tedious but demanding. Calutron operators watched dials for 8 hours, making minor adjustments to maintain optimal performance. Equipment failures were common, requiring rapid response to minimize downtime. Production quotas were relentless, driving continuous operation despite mechanical problems and worker fatigue. The compartmentalization meant most workers never understood what they were building. Calutron operators knew they were separating isotopes, but not what isotopes or why. Gaseous diffusion workers knew they were processing UF6 gas, but not its purpose. Chemical plant workers knew they were extracting elements, but not which elements. Only senior scientists, engineers, and administrators understood that enriched uranium would become atomic bombs. The workers who actually produced the material remained ignorant until Hiroshima revealed what their labor had enabled. The revelation of Hiroshima and Nagasaki, published in newspapers and magazines in August 1945, showed devastation on an unimaginable scale. Cities erased, buildings vaporized, human beings reduced to shadows burned into concrete. The images were visceral, undeniable evidence of what atomic weapons could do. Oak Ridge workers saw those images and understood that their technical labor, the careful monitoring of dials, the routine maintenance of equipment, the precise operation of complex machinery had made that destruction possible. By 1950, Oak Ridge had become a permanent fixture of American nuclear infrastructure. The wartime urgency had faded, but the Cold War arms race demanded continued production. Y-12 continued electromagnetic separation, now producing enriched uranium for weapon stockpiling rather than immediate wartime needs. K-25 operated continuously, with improved barriers and pumps increasing efficiency. New facilities were built for thermonuclear weapons research, isotope production, and nuclear reactor development. The population stabilized around 30,000 permanent residents. The temporary housing was replaced with conventional homes. The muddy roads were paved. The improvised infrastructure was upgraded to modern standards. Oak Ridge became a real city, though one dominated by federal facilities and security restrictions. It remained closed to casual visitors. Every resident required security clearance. The entire city existed to support nuclear weapons production and research. The technical achievements of Oak Ridge inspired similar facilities worldwide. The Soviet Union built its own uranium enrichment complexes, using gaseous diffusion technology derived from espionage and independent development. Britain developed electromagnetic separation and gaseous diffusion plants for its nuclear program. France built enrichment facilities for both weapons and civilian reactor fuel. China pursued centrifuge enrichment to support its nuclear ambitions. The enrichment technologies pioneered at Oak Ridge became the foundation of civilian nuclear power. Commercial reactors required low-enriched uranium, typically 3 to 5% U-235, rather than the 90% plus needed for weapons. The same gaseous diffusion and centrifuge processes developed for weapons production could produce reactor fuel. Oak Ridge techniques, declassified in the 1950s for civilian use, enabled the global nuclear power industry. The radiation exposure received by Oak Ridge workers remained classified for decades. Workers who operated calutrons inhaled uranium dust. Maintenance crews working inside diffusion cascades absorbed radiation from contaminated equipment. Chemical plant workers handling plutonium received doses exceeding modern safety limits by factors of 10 or more. The long-term health effects, cancers, radiation sickness, genetic damage, wouldn't manifest for years or decades. The government's response to worker radiation exposure evolved slowly. Initial studies minimized health risks, arguing that doses received were within acceptable limits. As evidence of radiation-induced cancers accumulated, the Atomic Energy Commission acknowledged some hazards but maintained that worker safety had been prioritized. Only decades later, after lawsuits and congressional investigations, did the government establish compensation programs for workers harmed by radiation exposure. The environmental legacy of Oak Ridge operations was equally problematic. Decades of uranium processing contaminated soil, groundwater, and the Clinch River with radioactive materials and chemical toxins. Mercury from isotope separation contaminated miles of waterways. Beryllium and other toxic materials leached into groundwater. The cleanup, begun in the 1980s and continuing today, has cost billions and will require generations to complete. The human cost of Oak Ridge extends beyond the workers who built and operated the facilities. The 3,000 families displaced in 1942 lost homes, farms, and communities. They were compensated at Depression-era land values, pennies compared to the strategic value of the site. Many fought legal battles for decades, seeking adequate compensation. Some never recovered financially or emotionally from the displacement. Their communities, small farming settlements with churches, schools, and cemeteries dating to the 1700s, ceased to exist, erased to make room for the atomic age. The strategic importance of Oak Ridge diminished as enrichment technology evolved. Gaseous diffusion, though effective, was enormously energy-intensive. Centrifuge separation, developed in the 1960s and 1970s, achieved higher enrichment with far less electricity. By the 1980s, centrifuge technology had surpassed diffusion, and Oak Ridge's massive K-25 plant was shut down. The building, once the largest on Earth, was demolished between 2008 and 2013, leaving only historical markers to indicate its existence. The electromagnetic separation facilities in Y-12 were similarly superseded. Calatrons, though effective for producing small quantities of highly enriched uranium, couldn't compete economically with centrifuges for commercial production. Y-12 transitioned to weapons component manufacturing, producing secondary components for thermonuclear weapons and processing enriched uranium for naval reactor fuel. The facility remains operational today, though its role has evolved from uranium enrichment to weapons component fabrication. The X-10 graphite reactor, shut down in 1963, was designated a National Historic Landmark. The reactor building, now a museum, preserves the facility where plutonium production techniques were pioneered. Visitors can see the graphite pile, the control room, and the remote handling equipment used to manipulate radioactive materials. The exhibits carefully balance celebration of technical achievement with acknowledgement of the human cost, both the workers exposed to radiation and the victims of Hiroshima and Nagasaki. The moral questions surrounding Oak Ridge and the Manhattan Project remain unresolved. Was the creation of atomic weapons justified by the necessity of ending World War II? Did the deaths of 200,000 Japanese civilians save hundreds of thousands of American and Japanese lives that would have been lost in an invasion? Or was the use of atomic weapons an atrocity, targeting civilians for mass death to demonstrate American power? These questions have no objective answers. They reflect fundamental disagreements about ethics in warfare, the value of enemy civilian lives, and the moral limits of military action. The workers who built Oak Ridge faced these questions personally. They took pride in their technical achievements, building the most advanced industrial facilities on Earth, producing materials thought impossible, contributing to ending the bloodiest war in history. But they also grappled with the knowledge that their labor enabled weapons that could erase cities, that the isotopes they separated became the cores of bombs that killed 200,000 people, that their routine technical work participated in genocide. Most Oak Ridge workers never spoke publicly about these contradictions. They returned to normal lives after the war, carrying their knowledge silently. Some became advocates for nuclear disarmament, arguing that the weapons they helped create must never be used again. Others defended atomic bombings as necessary evils that saved more lives than they cost. Many simply refused to discuss it, the moral complexity too painful to confront. The final accounting of Oak Ridge is statistical. 3 years of construction and operation, 125,000 workers at peak, $1.2 billion spent, more than the entire American automotive industry's annual output. 59,000 acres of Tennessee farmland converted to industrial facilities, 1 million cubic yards of concrete poured, 386,000 cubic yards of roads built, 10,000 miles of electrical wiring installed, 238,000 kilowatts of electricity consumed continuously, 1/7 of all American electrical production. All of this to produce 130 kilograms of enriched uranium and 6 kilograms of plutonium. Enough material for 3 bombs. Little Boy, which destroyed Hiroshima, Fat Man, which destroyed Nagasaki, and one test device, Trinity, detonated in New Mexico on July 16, 1945. 3 weapons that killed 200,000 people and ended World War II. 3 weapons that demonstrated power beyond anything previously imaginable. 3 weapons that defined warfare, diplomacy, and international relations for the next 75 years. The secret city America built to make one bomb became the birthplace of the atomic age. Oak Ridge proved that industrial might, applied with sufficient focus and unlimited resources, could achieve what seemed theoretically impossible. It demonstrated that American manufacturing capacity could be redirected from consumer goods to weapons production on a scale no other nation could match. It showed that compartmentalized labor could accomplish tasks beyond the understanding of the workers performing them. But Oak Ridge also revealed the costs of such achievement. Workers exposed to radiation without adequate protection. Families displaced from ancestral land without fair compensation. Communities erased to make room for secret facilities. Environmental contamination requiring generations to remediate. And the ultimate cost, the deaths of 200,000 Japanese civilians, killed by weapons produced in Tennessee by workers who didn't know what they were building. In 1985, on the 40th anniversary of Hiroshima, the Oak Ridge Historical Society organized a reunion of wartime workers. Thousands attended, many meeting for the first time in decades. They toured decommissioned facilities. They shared stories of construction and operation. They discussed the revelation of Hiroshima and its emotional impact. One speaker, an 82-year-old woman who had operated Caleutrons for 3 years, concluded her remarks with a statement recorded by local media. "We didn't know what we were building. We were told it would help end the war, and we believed it. When we learned about Hiroshima, I was horrified. I had helped kill thousands of people. But I was also proud. We had done something impossible. We had built machines that separated atoms. We had produced material that existed only in theory. We had contributed to ending the war." I've lived with that contradiction my whole life. Pride and horror, achievement and guilt. I don't know if what we did was right. I only know it was necessary. And that necessity required ordinary people to do extraordinary things without understanding what they were creating. The secret city America built to make one bomb produced 3. Those 3 bombs ended history's bloodiest war. They also introduced weapons capable of destroying civilization. Oak Ridge workers, following orders they didn't understand, enabled both outcomes. They remained proud of their technical achievements and haunted by their consequences. The thunder of splitting atoms, first heard in Tennessee in 1943, still echoes today, a reminder that human ingenuity can accomplish anything, for better or worse, and that the power to change history often rests in the hands of ordinary people who don't know they possess it.